I'm oral historian Mike Chappell. Today, June 16th, 2013, I'm interviewing Dr. Anna Taylor for the Endocrine Society at its annual meeting being held this year at the Moscone Center in San Francisco. Anna, would you tell me a little bit about your family background, beginning with your grandparents?
Gladly. Three of my grandparents are Viennese, were Viennese, and my maternal grandfather came to Vienna from Poland in 1900. My parents were Viennese, and my brother and I were born in Vienna. So both grandmothers had dress salons, and my maternal grandmother, Juliet Beck, was the dressmaker for the court of the Kaiser for one of the princesses, Princess Valerie. That was, of course, at the turn of the century. Between the wars, my maternal grandmother and my mother did a lot of traveling. They went to some of the famous beaches in Europe, Abacia, now called Opatia in Yugoslavia, part of the Austro-Hungarian Empire at the time. They also went to France, all the way over to Biarritz. They met quite a few Parisians and Americans, and during their travels to Paris, which they did so that they could copy fashions and bring them back to Vienna, they met a group of influential Americans who were very helpful in getting us affidavits to come to America. In fact, they had indicated, this was back in '33, when I was in utero with while my mother was in Paris, they had already indicated that we should really move out of Europe. We waited a while. And, well, my father was a mechanical engineering graduate of the Technische Hochschule of the University of Vienna. And this was after he had served in the Austrian army as a lieutenant and had been wounded on the Italian front. He opened a bicycle factory called Fulgur, which is the Latin word for thunder, a thunderbolt, or lightning. And he had this factory until 1938, when it was absconded by the Nazis. My father was imprisoned in October of '38, and immediately after he got out, my parents started the process of immigration to the U.S.
And where did you end up in the U.S.?
Well, we ended up in Cleveland. We came out of Vienna in '38. My brother and I and my mother and father and maternal grandmother, we came by a Holland-American line out of Rotterdam. Their ship, the Noordam, and we were in New York for 6 months, during which my father, in March of '39, got a position at the Murray, Ohio company in Cleveland. It was a bicycle company, so he was a draftsman with them, which fit right in with what he had been doing previously. My brother and I and mother followed him to Cleveland that June. So my brother John and I were schooled in Cleveland in the public school system, which at the time was excellent. And we were fortunate enough to have been selected for their major work program. This was a program rather unique. It allowed us to do conversational French in addition to all our other subjects, and we did that daily. We also did that every summer at Western Reserve University in their demonstration program for foreign language teachers that was organized by the head of this whole program, Dr. Emile Bay de Sauzet, and my French teacher, Therese Lamarca. And that was how we grew up. Well, my mother was wanted to make sure that we were heavily immersed in extracurricular activities. And so we had music lessons at the Cleveland Music School settlement, art school at the Cleveland Museum of Art, daily Hebrew classes, and a lot of sports. We did swimming, biking, tennis, and some of which I still do today as hobbies. And she also got me started on skiing when I graduated from high school.
Now, why did you choose to attend Radcliffe College?
Well, I applied to quite a few liberal arts schools and did pretty well in the admission process. Radcliffe had, the Cleveland alumni of Radcliffe College awarded me a scholarship, and that was probably the furthest from home and seemed the most interesting. So I went there. At the time, I was interested in majoring in languages and diplomatic work, but going to Radcliffe, the courses at Harvard Radcliffe in languages were all literature courses, and that was not my strong suit. So I switched into, fortunately, had taken a bit of science during that year, and then for financial reasons, returned home to Western Reserve University, Mather College, where I majored in chemistry and minored in biology and math.
Now, why did you switch to science? What was it about science that attracted you?
Well, science was always a forte, math in particular, and it was very appealing. And with the advice of friends and classmates who suggested that I go into graduate school, I in fact went to a summer school for a couple summers and graduated. I was able to get my bachelor's in 3 years and went on to graduate school in the sciences. And well, it was choice of medicine or research, and I knew I didn't want to practice medicine. So research in biomedical sciences.
Okay, we were going to pick this up with your time when you went for your PhD at Case Western.
Well, at the time, it was still Western Reserve University. More recently, they joined forces with Case Institute of Technology, and it's become one institution, Case Western Reserve. Well, again, for financial reasons, I stayed home while I was in graduate school, but fortunately, the basic science departments at Western Reserve were really very good. I picked physiology because it was the broadest of the basic science departments, and I applied there and was supported by a USPHS pre-doc fellowship throughout my graduate training. Among the physiology labs that had openings was that of Dr. Gordon Farrell. As a young MD, Farrell had trained with Evelyn Anderson at the NIH and had as a colleague Sam McCann, well-known endocrinologist. And Farrell's interest upon joining George Sayers was salt and water regulation, metabolism and regulation, and ACTH. I should mention that Sayers was an endocrinologist, and among other of his achievements was the assay of ACTH by the ascorbic acid method that he developed. So I joined the Farrell lab, and prior to my coming to the lab, they had already isolated from adrenal venous blood, aldosterone, the sodium retaining factor from the adrenal cortex. And they had provided evidence for a diencephalic center for the regulation of aldosterone. My project was to localize more precisely the area or areas of the brain which are involved in the regulation of the secretion of aldosterone. My first publication was in Endocrinology in 1958, and there I reported the effects of certain posterior diencephalic and midbrain lesions on aldosterone secretion in the cat. And the results seemed to evoke some controversy among well-known endocrinologists, Bill Ganong, J.O. Davis, Egdahl, and Barter. But my subsequent publication in Endocrinology in 1962 actually confirmed that there was a small region in the anterior midbrain and the posterior diencephalon and epithalamus that controlled aldosterone secretion. When we made lesions in the midbrain, we interfered with the secretion of aldosterone and in adrenal venous blood in the cat, and lesions in the epithalamus actually stimulated aldosterone secretion. And these studies formed the basis of my PhD thesis, Central Nervous System Regulation of Aldosterone Secretion. And it was actually gratifying to learn from the work of Dorothy Krieger and her colleagues. They had 2 patients who had tumors in this region of the brainstem, and these patients showed reduced aldosterone secretion and impaired salt and water balance. So, in essence, we found an area in the brainstem that suggested that there was a humoral factor for aldosterone secretion, and indeed Farrell's lab had some evidence for that. He and Bill McIsaac had isolated adrenoglomerulotropin, which specifically stimulated aldosterone secretion. They got it out of the rostral midbrain and epithalamus of dogs, and they tested it in the decerebrate hypophysectomized dog preparation using adrenal venous blood. They subsequently characterized adrenoglomerulotropin and found it to be a beta-carboline, a methoxyindole, a derivative of melatonin. Now, melatonin from the pineal had been isolated sometime before that by A.B. Lerner and his colleagues. We went on and isolated some more of these methoxyindoles, and one in particular, methoxytryptophan, was shown to inhibit the incidence of estrus and retard ovarian growth. As a postdoctoral fellow, I assisted in these studies from 1961 to 1963, supported by fellowships from USPHS and the American Heart Association.
Would you highlight what was known about the central nervous system and endocrine function prior to the 1960s?
Well, it had been known since the mid-30s that the central nervous system can influence endocrine function. And in the 1950s, actually, ACTH and the stress response became of major interest to neuroendocrinologists. Pituitary graft experiments that had been done by Jeffrey Harris in the 50s and Dora Jacobson showed that the anterior pituitary was controlled by substances released from the basal hypothalamus. And the groups of Guillemot and Shelley, they actually were looking for a corticotrophin-releasing factor beginning at about that time. CRH, corticotrophin-releasing hormone, was finally characterized by Wiley-Vale in 1981. Also in the 50s, neuroanatomical evidence for pathways from the midbrain reticular formation and to the diencephalon was being developed by Wally Nauta in the US and by Paul Dell in France, among others. But I realized that training in neurophysiology could enhance my career as a neuroendocrinologist. And I wanted very much to spend time in Europe, having been there briefly for the first time since 1938, on my honeymoon. At that time, I presented my doctoral research at the first International Congress of Endocrinology in Paris, in Copenhagen in 1960. I joined Paul Dell's Laboratory of Neurophysiology in 1963 as an advanced research fellow of the American Heart Association. The Laboratory of Neurophysiology was at Hôpital Henri Roussel. That was part of the psychiatric hospital, St. Anne's Psychiatric Hospital in Paris. This was an active place, a lot of stimulating work, stimulating environment, and it offered frequent interactions with Parisian and international scientists. Dell was also Secretary General of the International Brain Research Organization, which had been founded in 1961 and was part of UNESCO. So needless to say, we enjoyed Paris. Paris, with all its museums, its art galleries, and entertainment, was very exciting. My husband, Kenneth Taylor, continued his graduate studies in nuclear physics at the Orsay campus of the University of Paris, and he also immersed himself quite deeply in art, in particular Art Deco and Art Nouveau, which formed the basis for his very successful art gallery in Los Angeles subsequently. We also honed our fluency in French for our future roles as scientific translators. Dell and his two longtime colleagues, Drs. Martha Bonvalet and André Hugelin, were among the pioneers in our understanding of the midbrain reticular formation and its role in visceral, somatic, autonomic, and even endocrine functions. Baruzzi and Magoon in 1949 had called this portion of the central nervous system of the brainstem the reticular activating system because of their work and others that showed that one could get arousal by stimulating the reticular formation of the midbrain. It was, in fact, the nonspecific sensory system of the reticular core of the midbrain. But they called it the reticular activating system and will refer to it as RAS. So that was what Bonvalet had been working on extensively. And she had demonstrated that along with electrocortical arousal, you get motor and vegetative responses, and they're either phasic, short-lasting, or tonic, the tonic ones being mediated by the polysynaptic circuits in the midbrain reticular formation in the RAS. This is the work that I continued with her as a postdoctoral fellow.
I see. When you came back from Paris, you were appointed a professor?
Yes, I was. I was a newly appointed professor in Cleveland at Western Reserve University in physiology as an assistant professor. And at the time, I was one of 3 assistant professors hired. And much to my dismay, a bit later on, I found out that there was some pay inequity there. The 2 guys were getting somewhat more than I was getting. But anyway, having returned to Cleveland, I found that Gordon Farrell was no longer there. He had moved to the Texas Research Institute of Mental Sciences, which was affiliated with Baylor University College of Medicine. And he actually asked me to come along and move to Houston, which we did in June of 1965. So we had briefly been in Cleveland for a few months. And TRIMS, the Texas Research Institute for Mental Sciences, was part of the Department of Psychiatry at Baylor. Now, Baylor was an exciting place for neuroendocrinology, but it wasn't really in psychiatry. It was in physiology, where Guillemin had his home, and also in anatomy, where von Critchlow was conducting research. And being a basic scientist, I elected to join anatomy, and there I could partake in the teaching of anatomy as well. So this was somewhat of a new area for me, having been entirely in physiology prior to that.
And what did you, when you first set up your laboratory, what did you begin working on?
Well, I set up my lab at TRIMS and began experimenting on the role of the reticular activating system in the regulation of ACTH secretion. So adding another endpoint to the reticular arousal that we had obtained in Paris in terms of motor and visceral functions, and electrocortical arousal. We used the encephal isolate cat that we had used in Paris. I added to that cannulation of the adrenal vein so I could obtain adrenal venous blood for measuring cortisol. And also we had, we monitored blood pressure. And we found, not to our surprise, but we were able to show, in fact, that stimulation of the reticular activating system elicited a stress-type response from the animal, insofar as we got increased cortisol levels, and we got, in conjunction with cortical arousal, an increase in blood pressure, and we're able to show that the RAS is involved in mediating responses to stress.
So you got the results that they weren't surprising to you, but how did they relate to stress?
Well, of course, stress, we know, causes increase in ACTH and in pituitary ACTH and in adrenal steroidogenesis. Stress, in fact, affects health through its actions on diverse physiological systems, and there's a coordinated response to a stressor by most systems in the body that allows an individual to cope with the stressor and restore baseline activity or homeostasis. Now, the concept of homeostasis had been known since the mid-1930s, if not before that, and was certainly pushed by Hans Selye at that time. But more recently, Bruce McEwen made a distinction between the precise range of these homeostatic systems and the broader range of allostatic systems, where he considered allostatic systems as being adaptive, and they have much broader boundaries. So, and these allostatic systems enable an organism to respond to its physical state and to cope with the stressor. The primary allostatic response involves the HPA axis and the sympathetic nervous system.
What were the circumstances of your recruitment to the Department of Anatomy at UCLA?
Well, in 1967, my husband and I decided that we should improve upon the physical and cultural environment of Houston, and an ideal opening occurred at UCLA. Dr. Margaret Slusher, a prominent ACTH neuroendocrinologist, was just retiring from her position in the Laboratory of Neuroendocrinology that Tom Sawyer had set up, and was also housed in the Brain Research Institute. And she was also leaving behind their grant, which fit in perfectly with my own grant. Both virtually had the same title. Hers was entitled Central Nervous Control of Pituitary Adrenal Function, and mine was entitled Brainstem Reticular Formation, Function, and Stress. So I moved to UCLA, and it was certainly a wonderful environment. It was Tom Sawyer had this wonderful group of neuroendocrinologists that formed the Laboratory of Neuroendocrinology that he finally formed in 1981. And then there was the Brain Research Institute, which had actually been formed by reticular formation neurophysiologist Horace Magoon. So these were ideal places to be associated with, and as was the Department of Anatomy, which housed most of the neurophysiologists that were at the Brain Research Institute. The one shortcoming of my appointment was that it was a soft money position. And unfortunately, it remained that way for my for advancement through the ranks. But fortunately, I was able to do that. The times were right, and money was available, and so I succeeded in keeping soft money going throughout the years until I retired a few years back. So I set up a lab, or I took over Slusher's lab at UCLA, and we continued in our reticular formation and nervous system stimulation experiments into the role of the limbic system and reticular formation in ACTH regulation and stress. I briefly had an excursion into the pineal early on in my stay at UCLA. We were looking at electrophysiology of the pineal and how light would affect that and formation of melatonin. But that was not my main interest, so let me continue with along the lines of my main interest. Well, I made some progress in the early years, and at the 4th International Congress of Neuroendocrinology in Washington in 1972, we reported on some of our results stimulating various areas of the brainstem. We looked at the basal forebrain, and that happens to be quite an inhibitory area, and we obtained electrocortical signs of sleep, which correlated with inhibition of ACTH release. Again, as we were using adrenal venous blood in the encephaly soleil cat preparation. Well, then I was fortunate to have Dr. Matheson, Dr. G. Keith Matheson, who was more recently in the Department of Pharmacology and Toxicology at Indiana University School of Medicine. He came to the lab from Seattle, and he introduced the freely behaving cat preparation. So we had a cat that we had prepared with with electrodes in the cortex for recording EEG. There were also stimulating and recording electrodes in various parts of the CNS, in his case in the amygdala. Subsequently, taking this preparation to the rat, we were able to stimulate the hippocampus with then graduate student Dr. Robert Cassidy, who then went on to Texas Tech University. In the freely behaving cat, we also cannulated the jugular vein with an indwelling catheter down to the atrium, whereby we could collect peripheral blood and look at that for cortisol and corticosterone. And we then modified that preparation for the freely behaving rat. We did some work, we continued to do some work in encephalopathy Soleil cats, and we did that with Dr. David Lindsley from USC, where we looked at the subthalamus. So we had various regions that we could show from in the diencephalon and in the limbic system that we could show were related to inputs from the reticular formation. The hippocampus was, we showed some of those results were related to circadian rises in steroids. And at the time, it had been well established, the controlling mechanisms for circadian pituitary adrenal rhythmicity were of central nervous system origin. The generator being somewhere up in the forebrain or in the anterior parts of the hypothalamus. It was also known that the circadian pituitary adrenal rhythm is not present at birth, and that in the rat, it doesn't show up until the 3rd week of postnatal life. And we wondered whether we could modify the onset of the rhythm by giving ACTH or corticosteroids neonatally. We did that in conjunction with Dr. Robert Lorenz and a postdoc in the lab, and Dr. Barbara Bush-Turner, who was a graduate student at the time and subsequently went on to the East Tennessee University School of Medicine. And we found 2 critical periods where we could affect circadian rhythmicity. The first was during the 1st week of life in the rat. This is when hypothalamic regions were being formed, which are important for the circadian activity of the pituitary adrenal axis. And again, in the 3rd week of life, this is when some of the limbic system, midbrain circuitry, was being established. So these were 2 periods that we could modify by giving steroids early on in life. Well, a turning point in my career occurred in 1979 when I joined the Veterans Administration as one of its first group of alcohol research awardees. This was a program that had been initiated by Dr. Marcus Rothschild, an endocrinologist and a fellow interviewee of the Samhain Medical History Library. At the invitation of Dr. Arthur Uweiler, he was a VA and UCLA neurobiochemist, I set up my laboratory at the VA in his space in the psychiatry division at West Los Angeles VA. And I called the lab, had to give names to all labs. I called the lab the Alcohol Research Laboratory. It was not significant as such, but it had an identity. And at the same time, so I had 2 labs. I had the lab at the VA where we did our experimental work, and at UCLA, I continued to do steroid and hormone analyses with 2 very wonderful and able chemically trained research associates One was Marilyn Branch. She came with me from Houston and stayed with me until 1991 when she moved to Denver. And then I was joined by Miss Delia Teo, who is still with me today. And I turned my attention to the well-known actions of alcohol. After all, I had to justify my existence with the VA and on this Alcohol Research Award. And alcohol is known to be a stressor. And as such, it activates the pituitary adrenal axis. It's also hypothermic. And we use those two endpoints as they were very important to us in being able to continue our work on both adult alcohol exposure, both acutely and chronically, on fetal alcohol exposure, and more recently, in traumatic brain injury. So that's what I was doing at the VA for the last 30 years, and at the same time doing the same thing, more or less, at UCLA. We had found with a colleague, he was an anatomist at UCLA and also a psychiatrist, Dr. Emery Zimmerman, that neonatal exposure of rats, when they're exposed to morphine, that produces prolonged tolerance to this drug. And we wondered if neonatally exposed or perinatally exposed rats, if they wouldn't show prolonged tolerance to alcohol. And indeed, that's what we found. We found that prenatally alcohol-exposed rats, when you then challenge them with alcohol as adults, they show a hyper response, increased ACTH secretion, increased blood steroid levels, and they also show an increased hypothermia. So they're showing an increased response to alcohol. And, but not if we expose them postnatally. So our prenatal exposure was very exciting to us, and that got us into fetal alcohol exposure. And we pursued various aspects of fetal alcohol exposure and their response to alcohol, their response to other stressors from then on. You might call that fetal programming. And one wonders, why is it that environmental insults during fetal life produce detrimental long-term effects on the organism? Well, not only are there critical periods postnatally for the development of physiological processes, such as the neuroendocrine system, but there are also sensitive developmental periods during fetal life when many other physiological systems become organized or programmed, producing effects that may persist throughout life. With respect to the brain, we call this fetal programming, and it's dependent upon the processes of neurogenesis and apoptosis that constitute aspects of neuroplasticity. Fetal alcohol syndrome as such had actually been known since 1968. It was first described by Lemoine, a Frenchman. But we now know that it's basically one end of a continuum of fetal alcohol effects. And we now call this fetal alcohol spectrum disorders. Well, when one looks at fetal alcohol syndrome, as it was characterized in 1968 and as we've known it since, its characteristic features include craniofacial dysmorphologies, very typical, growth retardation, central nervous system dysfunction, and that manifests itself as mental retardation, cognitive and behavioral problems and impaired motor performance and communication skills. Well, in 1981, ours was really the first report on fetal alcohol effects in rats, granted, on the neuroendocrine system. And this was significant, not only because it was the first report and showed that FAE exerts persistent effects on adult responsiveness to alcohol, but also because it was the first indication that maternal alcohol consumption can produce hyper-responsiveness of the HPA axis to other stressors, not only to alcohol, in adult rats. And these other stressors that we had identified a bit later were opiate-mediated stress-induced analgesia and drug-induced hypothermia. And those studies were conducted with graduate student Dr. Linda Nelson, subsequently in the Department of OBGYN at Illinois University School of Medicine, and UCLA neuropharmacologist Dr. Norio Coca. And they've since been confirmed clinically, which was really gratifying to see. In addition to these pronounced and long-term effects of fetal alcohol exposure, which we'll call FAE, if I remember to shorten it, there are long-term effects on neuroendocrine and neurobehavioral systems. We showed with Drs. Dean Norman and Mei-Ping Chang at the West Los Angeles VA, and with Dr. Francesco Chiappelli of UCLA, that FAE caused impairments in T-cell development and function of the offspring. And we were among the first to demonstrate that. And again, it was very gratifying that clinical studies subsequently reported an increased incidence of infection in FAE subjects. Well, about this time, another layer of complexity arrived in neuroendocrinology, and that was neuroimmunology. Psychoneuroimmunology is the interdisciplinary scientific field that's concerned with the interactions among behavior, the immune system, and the nervous system. And it had been well characterized by clinicians and psychologists by 1990, when neuroendocrine immunology also became of age. Essentially, neuroendocrine immunology added this additional level of complexity when it became apparent that there is a reciprocal regulation between the central nervous system and the immune system, through which the CNS signals the immune system via hormonal and neuronal pathways, and the immune system signals the CNS through cytokines. Based on our finding that maternal alcohol consumption alters the development of the neuroendocrine and immune systems, we hypothesized that FAE would also interfere with this bidirectional communication between the immune and the nervous system of offspring. Dr. Razi Mia, currently a professor of psychology at the Hebrew University, while he was a postdoctoral fellow in my lab, started formulating concepts of sickness behavior, and he applied those to our fetal alcohol model. Well, fever is one response that's an important component of sickness behavior. Anorexia is another. And that response he was able to show was due to and he and others had shown, was due to the release of cytokines that serve to enhance the response of the host to infection. And what we did was we challenged our fetal alcohol-exposed rats. As adults, we challenged them with a pathogen known as a pathogen product, lipopolysaccharide, LPS. And LPS induces the formation of a cytokine, interleukin-1 beta. And we used that challenge and the formation of interleukin-1 beta as an endpoint in quite a few of our studies that we did subsequently. And this was relevant to the human condition because not only did experimental work show that LPS and IL-1 beta produce sickness behavior and had been pretty well characterized by that time. So when we applied this to our fetal alcohol model, we found that we had blunting of the febrile response to LPS. In other words, it made them sicker. And we also found that not only could we blunt the sickness behavior response, but when we gave LPS or interleukin-1 beta into the brain, intercerebroventricularly, ICV, this suppressed the hypothalamic content of the LPS-induced interleukin-1. So here we had a whole mechanism that we could show had been induced by the fetal alcohol exposure and now was present in adult animals some 2 months, certainly after they had gone through puberty. We went on to see if maybe it was the adrenal steroids that would modify this response, and indeed we found that was the case with Dr. Susan Tritt, a gynecologist. We were able to show that prenatal factors such as maternal adrenalectomy was able to prevent the blunted febrile response. Maternal adrenalectomy was able to prevent the blunted febrile response of adult males. But in the female offspring, it was the stress of developing control models, in other words, sham surgery during fetal life to the pregnant dams that prevented their blunting of the fever response. So this difference may well reflect the difference between males and females in the responsiveness of their pituitary adrenal axis, females being much more responsive. Well, we then ventured into adult alcoholism and the neuroendocrine immune effects of feeding adult animals alcohol. Our paradigm to produce dependence at the time was feeding alcohol for 14 days to adult animals. We fed it in an ethanol-containing liquid diet, and these experiments were again conducted in collaboration with Dr. Yermia and Dr. Horacio Romeo, currently of Argentina, and Dr. Paolo Prolo of Switzerland. And having done that and created dependence, we administered LPS, or the cytokine that it induces, one of the cytokines, interleukin-1 beta, and we observed blunting after this alcohol exposure of the febrile response. Now it's known that alcohol, it was well known at the time when we entered into this area, that alcohol is associated clinically with impairments of endocrine and immune functions and with increased susceptibility to cancer and infectious disease. So at least our experiments with LPS showed that we did, in fact, impair the neuroendocrine immune response. We also were able to show that the circadian increases in body temperature and activity that normally occur during the dark phase in rats were blunted in this alcohol-fed model. And these studies provided evidence for impairments of neuroimmune function following chronic alcohol consumption, and they may well be associated with the HPA axis, as had all at the same time been shown by Dr. Catherine Riviere. Indeed, with postdoctoral fellow Dr. Ava Rede, who is now professor of psychiatry at Northwestern University, we provided in vitro evidence for the direct effects of ethanol on ACTH and CRF release. Well, given the considerable evidence suggesting an association between alcohol consumption and increased cancer risk, we collaborated with my colleague in the Department of Psychology, Dr. John Liebeskind, and his group of graduate students and postdoctoral fellows. Interestingly, John had been a postdoc at the same time that I was in Paris. He was in the neurophysiology lab of Dr. Albé Fassard while I was with Paul Dell, and there I actually had met John prior to my coming to UCLA. So with his group of students, postdocs, we studied the effects of both acute and chronic administration of alcohol on tumor progression and metastasis in rat models using leukemia and breast cancer as endpoints. Our results indicated that facilitation of tumor progression is related to ethanol-induced impairment of the normal tumor-killing activity of NK cells, and that interaction between NK cells and tumor cells. We did additional studies with Dr. Shamgar Ben-Eliyahu, who is now professor of psychology at Tel Aviv University, and Gail Page, professor of nursing at Johns Hopkins. We showed that estrus-dependent alterations in the number of large granular lymphocytes that contain NK activity, these cells, those alterations suggested a diminished NK activity for each per cell during two phases of the rat reproductive cycle, the proestrus and estrus phase in the female rat. And these are the same phases that were characterized by higher susceptibility to metastatic development. The effects of sex hormones can be mediated by our interaction with the differing stress responses of males and females, and may well have implications for the surgical management of breast cancer, some of which has been applied to human subjects in recent years in terms of the role of estrogen. Postdoctoral fellow, Dr. Deborah Hodgson, now director of the Laboratory of Neuroimmunology at the University of Newcastle, Australia, and Dr. Raz Yirmiyah also demonstrated that interleukin-1 beta acts centrally via prostaglandins to suppress NK cell activity and impair clearance of tumor cells from the lungs. So these studies substantiated the risk factors involved in alcoholism and cancer. Well, traumatic brain injury patients show a profound acute phase response, which is hyperthermia. And we know that hyperthermia after traumatic brain injury is associated with poor outcome. So there have been trials off and on in the last decade to reduce that hyperthermia that occurs right after traumatic brain injury. We tried doing that in a rat preparation, and our rats we do traumatic brain injury by cortical contusion injury, which is done stereotaxically in rats, anesthetized rats, and then they wake up from that. And we monitor their temperature with an implanted telemetry capsule, which monitors body temperature. So we're able to show that, yes, they do have hyperthermia after traumatic brain injury. Well, we looked at that, and we thought that maybe by giving alcohol to adult rats before they got their CCI, their cortical contusion injury, we might be able to diminish that hyperthermia and have a protective effect on their brains, a salutary effect. Well, yes, in fact, we found some of that. But let me go back a moment and indicate how I got into this in the first place. Well, I had a colleague with whom I was been teaching, Dr. David Havda, and since 2000, with his encouragement and support, he's been professor of neurosurgery, and he's director of the Brain Injury Research Center of the Department of Neurosurgery. Been able to substantiate this hypothesis about alcohol. In fact, some of his colleagues were doing alcohol research and showed neuroprotection clinically. So we did that. And let me just say that TBI and its sequelae are major burdens and hazards in military medicine, as well as in general public health. Alterations in endocrine and immune function and in neurobehavioral processes, such as the sleep cycle, circadian rhythms, have been observed not only in animal models, but in human clinical studies of patients with traumatic brain injury. So we wondered whether TBI would produce alterations in the neuroendocrine response of the HPA axis to a stress challenge. And our recent experimental data indicate that TBI does produce lasting dysregulation of the central substrates for coping with stress. And this has relevance to treatment, therapy for TBI patients, and perhaps also to post-traumatic stress disorder, which is so common in these situations. Doctors Cheyenne Rahman and Richard Sutton of the Department of Neurosurgery and I have reported differential effects of CCI severity on the corticosteroid response to restrained stress that persisted for 70 days after CCI in the rat, which is a long time. These are adult rats that are getting the CCI, and now they're well past, well into adulthood, and they're showing this effect. We found that mild CCI resulted in an enhanced response, but became more interested in the response to moderate CCI, where the stress response we found was attenuated. We suspect that these differing responses may be mediated by differential effects of mild and moderate CCI on the efficiency of glucocorticoid negative feedback, or signaling, among hypothalamic and extrahypothalamic components of the neuroendocrine stress response system. Indeed, in following up on the attenuated stress response of the moderate CCI group, we found that their sensitivity to glucocorticoid negative feedback was enhanced, along with greater hippocampal cell loss, but not altered pituitary responses to CRH. Furthermore, as we could restore the neuroendocrine stress response with antagonists of the glucocorticoid receptor or GABA receptor, it appears that suppression of the stress-induced HPA response after moderate CCI is mediated by the inhibitory actions of glucocorticoid receptors and the neurotransmitter GABA. Furthermore, moderate CCI led to a loss of inhibitory neurons in regions of the hippocampus and amygdala, brain regions with neural pathways that affect limbic stress integrative pathways. We are currently assessing the effects of moderate CCI on the neuroimmune component of the stress response.
Would you talk a little bit about your service in women in neuroscience and the Association of Academic Women at UCLA and maybe Association of AWIS?
Well, early on after joining UCLA, I became affiliated with the Association of Academic Women at UCLA, and that basically reawakened my awareness of the gender bias faced by professional women and that I had encountered in terms of salary inequity as early as my first academic appointment. So I was on various committees. I was on the executive board of the Association for Women in Science, which had been started in 1971 by Nina Schwartz, endocrinologist, also Samhain interviewee. I was on that executive board in 1975. I became a member of the American Association of the Anatomists Committee on Women and Diversity and other societies to which I belong, the Society for Neuroscience. I chaired and have been on several of the committees of UCLA and its academic senate on women and diversity, women and minorities and diversity, and I was president of UCLA's Association of Academic Women. To my mind, aside from the collegiality that such membership engenders, these committees function primarily as monitors and watchdogs of the ongoing problem for women and minorities. The fact that there has been slow but steady progress in recent decades in the status of women and minorities points to their effectiveness and their importance. But interestingly, a recent issue of Nature, the March 7th issue of Nature, in its focus on women in science, reported, and I quote, that science remains institutionally sexist. U.S. universities and colleges employ far more male scientists than female ones, and men earn significantly more in science occupations. So much remains to be done by these committees. They need to continue to apply pressure at all levels of the institution.
Do you want to talk a little bit about your service in terms of the Winter Conference for Brain Research?
This was a conference that I and a group of other neuroscientists from UCLA, from the West Coast, who enjoyed skiing, started back in 1968. We skied during the daytime, in between our morning scientific session and our afternoon and evening scientific session. So we didn't disregard science, but we did enjoy skiing. The WCBR continues to this day. It's got 500 or more neuroscientists attending from the US and abroad. In 1970, at its third meeting in Aspen, Snowmass, Colorado, I was bold enough, having been a ski groupie in Cleveland, to ask, well, what about our discounts? Don't we get discounts on lift tickets and housing and whatever? And I was told, well, if you want to pursue that, you have our blessing. So I did. And I was facilities chair along with my husband for 20 years. We kept the conference going, and it was a lot of fun. We also started a European Winter Conference back in 1979, helped them start that, and that's still going. So it's been a good contribution.
Now, how about your contribution? You were appointed by the White House?
Well, yes, that was an unexpected highlight of my career. I was nominated by NINDS to head the U.S. delegation of the Economic Summit Countries International Conference for 1986. That conference was on neuroscience and ethics, and it was held in the Federal Republic of Germany at Klostergut Jakobsburg in April of 1986. My appointment came from the White House's Office of Science and Technology. The conference was hosted by the Max Planck Institute for Advancement of Sciences and by Chancellor Helmut Kohl, and then President of the Federal Republic of Germany, von Weizsäcker. I was the only female delegate, and that had an advantage insofar as at Chancellor Kohl's lunch, I was seated between him and our US Ambassador, Richard Burt. And I might say I did some translation between them in German. Perhaps not necessary, but well received. And I sat next to von Weizsäcker at dinner at the conference one evening. That was the first such annual conference for scholars in how neurosciences impacts, how the life sciences impact mankind for the summit countries. And we strongly recommended that these conferences continue. I'm not sure they have. I would be interested to find out if, in fact, they did continue.
Would you like to comment on this current views, your current views of the field?
Well, PNEI, Neuroendocrine Immunology, PNEI, is the study of interactions among behavior, neural, and endocrine function and immune system processes. Now, contrasting that with the disciplinary analyses of the mechanisms that govern the functions of a single system, PNEI studies the relationship among all these systems. Despite current emphasis on cellular and molecular biology, to my mind, PNEI's integrative approach to studies of neuroendocrine immunology is paramount. I think it's not really possible to obtain a full understanding of endocrine and immunoregulatory processes without considering the organism as a whole and the internal and external environment in which the adaptive responses of this system takes place.
Thank you.